At 50 degrees Celsius, conventional machines do not just struggle, they fail. Sand devours electronics, traction disappears, and standard engineering hits a dead end. Yet a new generation of desert machines is doing something extraordinary. Hovercraft gliding dunes, robots hopping across sand, autonomous convoys with no drivers. These are not upgrades, they are ingenious inventions redefining what engineering can accomplish. But first, you need to understand why the desert destroys everything we build. Arid regions present a compound mechanical threat. Standard lubricants turn into grinding paste when mixed with fine quartz dust, which measures down to a few microns. This microscopic debris easily bypasses heavy seals, wearing down bearings and shorting out internal circuit boards. On the ground, intense solar radiation drives surface temperatures past 60 degrees Celsius, cooking power electronics that struggle to shed heat. Below, the loose, unstructured sand offers almost zero shear strength. Tires spin helplessly, converting forward energy into sinking ruts. Compounding this physical toll is the sheer scale of the environment. Without physical landmarks, traditional optical and inertial guidance systems drift, leaving systems blind. When service depots are hundreds of miles away, any small mechanical failure becomes an immediate, permanent loss. To survive here, engineers cannot simply build stronger parts, they must rethink mechanical physics itself. Countering loose, shifting sand requires basic mathematics rather than raw horsepower. To prevent a multi-ton machine from sinking, engineers increase the contact area between the vehicle and the ground. This distributes the heavy mass, reducing ground pressure to a fraction of a typical truck's footprint. Replacing standard tires with wide, continuous tracks distributes weight evenly across the sand ripples. In field tests at the Yuma Proving Ground, the PowerBully Tracked Dump Truck applied this logic. By using 750 mm wide tracks, it maintained a ground pressure of just 0.6 kilopascals, roughly 1/10 that of a conventional truck, allowing it to climb 30% sand grades at 12 km per hour. For extreme payloads, the Russian DT-Vityaz uses an articulated dual body design. Spanning multiple axles with continuous belts, this 800 horsepower machine exerts a mere 0.5 kilopascals of pressure, literally floating over unstable dunes. But spreading the load this way demands massive engineering sacrifices. Articulated joints, complex hydraulic systems, and constant track tensioning mechanisms must endure relentless sand abrasion, resulting in high maintenance costs and intense mechanical upkeep. Segmented skirts strap a pressurized air cushion just centimeters above the dunes, allowing hovercraft to bypass sand friction entirely and glide at 37 km per hour. For vertical barriers, the tiny Salto robot uses a spring-loaded leg to store and release elastic energy. It clears obstacles taller than its own body in a single bound, bypassing rough ground that halts traditional tracks. Expanding on this, wheel-leg hybrids combine speed and climbing agility. These systems roll across hard-packed stretches, then instantly switch to step over loose drifts and steep ridges. Even the howling desert wind becomes an active tool. Wind-propelled land yachts use rigid carbon composite wing sails to turn strong breezes into forward thrust, propelling streamlined rigs across dry lakes at over 200 km per hour without a drop of fuel. These radical platforms prove that navigating the desert is about rewriting the physics of motion from the ground up. Even if a machine successfully crosses shifting dunes, the survival of its cargo remains a separate engineering challenge. In the desert heat, sensitive cargo like medical supplies can degrade within minutes. This has transformed cargo from a passive payload into an active, self-contained engineering system. At the center of this logistics shift are modular payload pods designed to isolate goods from the elements. Systems like Zipline's R2 pod are built specifically to endure these brutal environments. Each container is sealed to an IP67 rating, making it completely dust-tight against ultrafine sand while providing up to 2 hours of passive thermal hold in extreme heat. But keeping cargo safe inside is only part of the equation. Transferring these goods in a sandstorm requires automated dock and handoff logic. Instead of human operators exposing the cargo to the elements, automated ground pads mechanically latch the pods upon landing, maintaining a sealed environment throughout. Embedded RFID antennas instantly read the pod's unique identifier to update inventory tracking without opening the container. By treating the cargo container as an engineered interface, logistics platforms bypass the environmental hazards of manual handling, proving that desert survival is as much about how goods are packaged and transferred as it is about how a vehicle drives. Coordinating these deliveries across vast, featureless spaces requires a synchronized network rather than isolated vehicles. In the Permian Basin of West Texas, Kodiak AI operates the Dune Express, a driverless logistics network that has completed over 100 automated sand deliveries. These 18-wheelers navigate a 21-mile off-road route without a driver in the cab, braving high temperatures and low visibility dust storms. To maintain a tight, safe formation, the fleet relies on leader-follower control. Low latency, vehicle-to-vehicle communication links the convoy, sharing telemetry with response times under 100 milliseconds. When the lead truck encounters a patch of soft sand, its sensors register the traction loss and instantly broadcast steering and throttle adjustments to the trailing vehicles, preventing them from bogging down. To close the final gap where heavy trucks cannot tread, the system transitions to a drone-ground hybrid model. Fixed-wing autonomous drones launch from regional hubs, dropping IP67 rated payload pods precisely onto automated ground stations. In the remote Sahel region of Chad, where sandstorms routinely swallow roads, this layered, driverless supply chain is already becoming a lifeline. By bypassing driver fatigue and impassable terrain, these synchronized networks bring reliable medicine, food, and equipment directly to isolated desert communities and remote field operations. A machine's physical endurance means nothing if its power architecture fails. In these harsh environments, flexible solar arrays integrated into a vehicle's skin represent the most reliable energy strategy. In March 2026, NASA's Ernest rover proved this during a 37-hour, 16-mile autonomous run through the Colorado desert, relying on a solar-assisted battery system. For heavy-haul transport, hydrogen fuel cells offer extended range, though their thermal management remains a steep hurdle in extreme heat. Engineers also try to harvest kinetic energy, but loose sand degrades the efficiency of regenerative braking. On unstable dunes, energy recovery drops below 30% under moderate braking. In the desert, energy is a strict mathematical budget. An overheated electrical system or a sudden power deficit ends the mission just as permanently as a broken axle. Survivability in extreme environments relies on a layered, active defense. To protect heat-sensitive electronics, engineers deploy high reflectivity thermal shielding and liquid coolant loops. If a vehicle tips, active rollover mitigation systems deploy, while a redundant navigation suite fuses a high-precision inertial measurement unit with visual odometry and satellite fallback to maintain tracking through blinding dust storms. This links sensing and mobility into a continuous safety sequence: detect, slow, stabilize, and recover. Future designs extend this protection with biomimetic hulls inspired by sidewinder snakes that reduce fine-grained sand adhesion, morphing suspension systems that rapidly adapt on the fly, and polymer abrasion-resistant coatings. Yet, a vast divide separates laboratory prototypes from active, commercial deployment. While lightweight wheel-leg platforms remain confined to controlled testing environments, heavy machines like $2 million tracked carriers are already fully operational. Ultimately, the transition from prototype to field deployment is governed by strict real-world filters, high acquisition costs, intensive maintenance demands, complex localized infrastructure, and the environmental footprint left on fragile desert ecosystems. As extreme environments expand across the globe, these ingenious designs are no longer just niche experiments. They are the blueprints for a changing planet, proving that breakthrough engineering doesn't just conquer nature, it redefines what's possible. Which of these machines redefined your perspective? Let us know in the comments.